Hello, we are Team ME28. I'm Richard Soria.
I am Nicholas Neal.
And I am Shuhan Huang.
Our faculty advisor is Dr. Najat Olgach, and our industry advisors are Michal Subielski, Bruce Hansen, and Jerry Fennerty from ID Mail Systems.
Our project statement for this project was to create and design concept for a parcel sorting mechanism. Currently, ID Mail provides mail solutions to clients that require package and parcel movement systems. A typical parcel movement system can consist of many stations, including weigh stations, label scanning stations, and sorting. ID Mail would like to develop an innovative parcel sorting system that will distribute packages to the appropriate locations.
Our deliverables are the design of a parcel sorting mechanism and the assembly of the prototype. In terms of requirements, the sorter should be equipped to handle packages ranging from 50 grams to 10 kilograms. The sorter also needs to be able to sort anywhere from 5,000 to 30,000 parcels over an 8-hour period. We also want to keep the cost of this sorter low so that it is cost effective for the sponsor.
So before beginning the design process, we did some background research and investigations into current sorting methods widely used on the market. Some of the most common ones we found were the push tray, pop-up roller sorter, embedded roller sorter, and tilt tray sorters. We also came up with a personal design which involves a bit of variation and adaptation from current state sortation technologies. We ended up choosing one of the personal design variations with some recommended adjustments. We chose a design that involves a conveyor attached to an axis of rotation just under the side of one conveyor. Then the entire conveyor itself would be lifted with the use of a pneumatic piston. This would allow the package to slide off the side of the conveyor and be properly sorted.
Once the research process ended and we decided on a specific design idea, our team began to work on modeling the system in SolidWorks. We had quite a few variations of the design since we made changes over time. When we first started modeling, we didn't have individual parts for the assembly in SolidWorks. We just had very rough sketches of what a potential conveyor system could look like. The first designs were basic extrusions that would represent the parts that we would be adding in at a later point in time. In the left and in the center images, you can see what the designs looked like towards the end of the fall semester. At this point, we envisioned the system resting on two separate tables on either side of the conveyor. With the help of the sponsor, we determined that it would be best to have the conveyor supports be a single and connected frame instead of two separate ones. We also considered the possibility of designing a chute to be placed on the side to catch packages, but decided to focus strictly on the design of the conveyor. The image on the right-hand side has an image of the design about halfway through the spring semester with the single frame design we settled on.
Once the actual design process began and we started to have a more constructed version of our design, we started to look into the sizing of the shaft, specifically finding the diameter of the shaft that would be used as the axis of rotation. To do this, we used the torsional equation and plugged in the numbers for the twisting angle, length of the shaft, and modulus of rigidity. And after plugging in these numbers, it was found that the diameter of the shaft would be 22 millimeters.
For the piston selection, we used two equations to select a suitable piston. The first equation is that the power factor times 1.5, which is the safety factor of piston, equal to pi over 4 times the square of bore diameter of the piston. The second equation is that the force provided by the piston equals to the pressure times the power factor we found in the first equation. By putting the technical specifications of different pistons into these two equations, the force provided by the pistons can be calculated. Then we compare the calculated forces with the required force to lift our design. Therefore, a suitable piston was found.
These images show what the final design looks like. The shaft is attached to the frame via the pillow block bearings and allows for the conveyor portion to rotate around the shaft. Several additional features were added to make it possible to build and possibly test as well. This includes the feet that we added for stability, blocks to hold the mounting brackets for the conveyor rollers, and attachment points for the cross-sectional extrusion that will allow for the attachment of the piston to the conveyor. The movement of our system in SOLIDWORKS is shown in this video. Through the help of our sponsor, we identified various suppliers for the different parts of the design. For the frame, we used aluminum extrusions that would be able to hold and support the structure. In addition, we ended up deciding to use rollers that had self-contained motors to facilitate the design. The rollers and the brackets would end up being about 70% of the design costs.
So we were able to do sufficient background research into existing technologies for sorting mechanisms. From this, we gathered various potential design ideas and combined concepts into one functional design idea. We modeled the conveyor in SOLIDWORKS roughly at first and began to come up with an actual possible design. We evaluated the functionality of different ideas and made changes to the design, narrowing down and eliminating as many possible issues as we could. Although not assembled, we believed that if assembled, this design would be functional and it would be able to properly lift and sort packages.
We would like to thank our sponsor, as well as our advisors for their assistance along the way in this project.